We have few more minutes to commence our lecture, very few more minutes to 9 a.m. when the CHE 176 class is supposed to commence. So I welcome Isa Rachel Bamidele, Miracle Abraham, Emmanuel Uniyide. Great. Nice to have these ones and others that will be joining us very, very soon. I pray that today I can have minimum of 1,000 of you attending this lecture. You are supposed to be like 1,700. So if you are sharing, no problem about that, but make sure you are not cheated. That's the most important thing. Like I normally say, get your writing materials to participate in the lectures, your lecture notes, Chemistry 176, even though it's on YouTube, you can always listen to me at your convenience anywhere in the house and anywhere in the world. And at the same time, you can access all the lectures we have been having through the YouTube and the LMS platform. Once more, I welcome you all. I'm sure that today is going to be highly memorable and commendable and full of success, and you will all gain tremendously more than your expectations. God will make it possible for you to be successful and understand all we're going to embark upon to study by the grace of God in Jesus' name, amen. Now, straight off to our point, and well, just a minute or two before 9, make sure you register yourself, your identity, your matric number, most important, with your names and departments, and just hi me. I hope you are hearing my voice. Good, if you are hearing my voice, you can just hi me, ma. Everything is perfect. I'm hearing you, you're communicating, and I'm also okay here. That's all. I need to know that you are good there, so that I can also be happy that you are good. I'm good too. So, and that is why God is so wonderful. It's made it easy for all of us to gradually be moving on amidst the so many challenges in the nation and world in general. Well, I will be rounding up my lecture after today, and Dr. Abwaba will be taking up as from next week, the same time, same links. So be there for her too throughout. As you have cooperated, please cooperate with her too. And if peradventure we finish up and there's still time, I don't mind coming up, especially maybe my second lecture when there was many of you disobeyed, you didn't unmute yourself, sorry. You didn't mute yourself and there were lots of background noise and I'm not too sure you gained. I was perplexed myself, so maybe I have chance, I'll repeat that lecture again. I think it's on ethers, the chemistry reaction preparation for ethers. If possible, we'll do that. Or just access the PowerPoint, which is on the LMS. Let me say that the PowerPoint for the carboxylic acids and derivatives, which I placed on the LMS, is highly incomplete. You are supposed to have like 43 slides. But when the LMS platform was complaining that it's too heavy, I had to drop a lot of figures and pictures, which so that I can give you something before the lecture today. So this YouTube, the PowerPoint slides is the updated and better one. You can discard the one on the LMS, except it allows us to place this one there. So we go straight to our lecture. I'm happy to tell you again that we are in for, Chemistry 176, Organic Chemistry 1. And by the end of the course, I'm sure anywhere in the world you are, you should be able to understand organic chemistry at whatever level, especially if you can make this Organic Chemistry 1. I bet it with you, you can cope with organic chemistry anywhere in the world at whatever level, even up to PhD or professor or whatever stage. Now, like our normal norm, we will be considering the chemistry of carboxylic acids. I'm going to shorten as COH and derivatives. We have done some introduction. I'll still do some introduction to its chemistry a little bit or remind us So those first two bullets, we have actually touched a little. That's good. Thank you for telling me that you are all good. Nomenclature, we have one, how to name carboxylic acid. We've done that earlier, even it was specified or allotted to a lecturer to do that. Those are elementary aspects, but very important for our work. So we commence as from the third bullet here, where we'll be considering the uses, properties, importance, applications of carboxylic acid. Actually, they are interwoven, so we'll be coming across them. Specifically, too, we'll be going deep into the preparation or synthesis, how we obtain these carboxylic acids and their derivatives. And then we'll be checking on the chemistry and reactions of this carboxylic acid. I'm sure from the introduction to its chemistry, which we are going to commence very soon, you'll be able to come up with cogent information on the chemistry of carboxylic acid and derivatives, and you'll be able to predict reactions and know trend of events under these carboxylic acid and derivatives. You don't need to memorize as such. Once you go with what are the protocols in the chemistry of carboxylic acid and derivatives. So we'll also be checking on about 4 derivatives of carboxylic acid. I'm happy that carboxylic acid is not strange to you. You've started coming across them from GSS. I could have even said from primary school, because you eat a lot of unripe mango. Some of you are naughty. And then when mango is coming up, you go and pluck unripe mangoes. You have a lot of these carboxylic acids and then naturally occurring. You take your palm oil. In the palm oil, you have palmitic acid, which is also a naturally occurring carboxylic acid. So you are used to these ones. I love trying to get a good foundation so that we can continue to build on. So this topic is not really strange to you. You've been coming across them. Even the derivatives too, you've been coming across them. We treated some when we lecturing ourselves on that decarbonize. So let's go straight into work. Now, this is how we're going to consider the chemistry of carboxylic acid, which we are introducing ourselves into, or rather how we're going to consider the lecture today. If you don't write anything, you can write these bullets. Once you have it, it's going to give you direction. More so, you have the YouTube near you, so you can always have it. I want us to start with the structure. Let's have a very close look at the structure of carboxylic acid, general structures, and then the implication of hydrogen bonding, which is depicted from the structures. We'll move straight to the physical properties, which is very, very essential. So you can't miss all these in exams, short questions, but applying questions. And then we go straight into how we obtain them in 2 big perspectives: industrially, that is economically or commercially, how we prepare this carboxylic acid. Immediately we go to how we synthesize them in the laboratory. We have a number of that over here. We're going to pick on each of that: preparation through oxidation of primary alcohols. You know that one, the trend from hydrocarbon, which is especially straight chain unbranched, you oxidize, you get your primary alcohol. From primary alcohol, you oxidize further, you get your aldehydes, and then the oxidation will not stop. You know, all this we did under the chemistry of aldehydes, it will finally give you your carboxylic acid. So that's more or less like revising what you have done before. And this aspect of Grignard synthesis is very, very important, where you react CO2 with appropriate Grignard reagents, and then you have additional carbon coming up as the carboxylic acid functional group on that substituent that has your RNGX, either Br or iodine or sometimes chlorine in the Grignard reagent. Go and revise those ones. We'll also go into hydrolysis of nitrites, and simple hydrolysis of nitrites to give you the same number of carbon-containing carboxylic acid derivatives. Hydrolysis of esters involving saponification, you have that one. Oh, Cannizzaro reaction is a name, is the reaction targeted at the kind of redox reaction. We're coming there deeply. So by the time I come there, also you've had it before, I expect you to have checked on some of these things. It's a kind of redox reaction whereby you react with sodium hydroxide, and you have both reduction product, the alcohol, and also the oxidized product, which is the carboxylate, being formed from here. Then we have the synthesis of benzoic acid from methylbenzene, that's just mere oxidation. And we can see this straight off. And also we see some synthesis preparation of some derivatives like the amides and the rest of them. Even under reactions too, we see the formation of some of these derivatives, acyl compounds and whatever. Then we end up with the derivatives. Those four I told you about is acid chloride. We touched some the other time. Anhydrides, you should know their general formula now, esters and amides. So we go straight into the lecture proper. Yes, we want to touch on the structure immediately after. We're going to look at, we're going to check on the hydrogen bonding in the structure. Yes, as you will see, as seen in other carbonyls, there is this carbon-oxygen double bond, carbonyl functional group, as seen in other carbonyls. This ones, there is mesomeric withdrawal of electron. Let me not start putting some carbonyl here. That's just what I mean. But or the carbonyl section in other carbonyls, and when we talk of carbonyls, we're talking of let me just edit this quickly. And well, just because I want you people to understand the elementary things, but it's not too rigorous. So anytime you have this carbon-oxygen double bond is a carbonyl. We've seen it in carbonyls, sorry, we've seen in aldehydes, we've seen in ketones, it's in anhydrides, it's in, it's also in our food system, like our carbohydrates, always having carbonyls. They are all scattered naturally, synthetic and whatever. And specifically, even carboxylic acid, we have this. Now, at that region where you have the carbonyl, there is this mesomeric withdrawal of electrons from the pi. The pi electrons are what is happening here. But let's look at the direction at which the withdrawal of electron is going. There is withdrawal from the carbon atom of the carbonyl, which the pi electron spends more time on the oxygen of it, and that is it. So making that carbon of the carbonyl slightly positive, and then the oxygen of the carbonyl slightly negative, more electron rich. This is more electron deficient. And you know that when something is electron deficient and a nucleophile, a nucleus-loving material, we want to attack that center. That's simple chemistry of carbonyl compounds, which we treated under ketones and aldehydes. Now, definitely, yeah, it's electron rich. So electrophilic attack, we love to do that. But meanwhile, let's just cut it like that. That's simple electrophiles, nucleophilic attacks, which I think Professor Shu never handled you on. And the other side of it, we have the inductive, because of this positive effect, it results in inductive move of electron from the hydrogen of the OH towards that carbon that is electron deficient. So in other words, this hydrogen can easily leave as a proton. So you have a kind of RCO double bond and then single bond O minus, and that one can also be distributed. Well, let me go back to what we have. It's quite interesting. I've seen in other carbonyls, aldehydes, ketones, etc. There's mesomeric withdrawal of electrons from away from the carbon atom of that carbonyl towards the more electronegative oxygen atom in the carbonyl bonding of carboxylic acid. This leads to a relatively positive charge on the carbon atom, and that's the figure below. Electron deficiency on that carbon now results, that is the carbon of the carbonyl, is what is the causative agent that causes inductive pull of electron away from the hydrogen of the OH bond. So, and we are showing the structure already. We've shown that. Now, the structure from what we have seen, this intensifies the stability of our carboxylate ion. And you can see the carboxylate ion gets, we try to see how it will remain stable. Therefore, you enhance, in order to become stable, there's the removal of this hydrogen through that inductive effect, and it leaves just like a carbon, sorry, like a proton, H+. This is not the case in alcohols, which also have OH, where it is more difficult to remove its own proton, but it's easy to remove the protons in this carboxylic acid derivatives and carboxylic acid. So hence, you have weaker acidic property compared to carboxylic. And in case you are considering acidity, OH alcohols are weaker than carboxylic acid from this perspective, because from your elementary chemistry in your GSS, they taught you a name material that can furnish hydrogen ion, hydrozonium ion is known as an acid. So that is it. So carboxylic acid are able to furnish that proton, hydrogen plus, more than alcohol. So that's why it's more acidic. The carboxylate anion exists as a resonance hybrid, and that we're going to see in the next picture, where you have the pi electrons being delocalized between the two carbon-oxygen bonds, making them now look so equivalent, and that's the end product. That's why I use a forward-back reaction or arrow to show that this is now making it equivalent. The CO is like 1.5 double bond, and like that, that's something like that. And then we move to the hydrogen bonding section of this. What's the implication of this hydrogen bonding? Please listen very well, class. The simplest carboxylic acids, that is the first members, you know what methanoic acid is. Another name for methanoic acid is formic acid. Don't forget your formaldehyde too is the simplest aldehyde. So the next member is ethanoic acid, also known as glyceracetic acid. We'll be talking about this very soon. So this simplest carboxylic acid, they usually exist as a dimer. Can you say that, everybody loud where you are? They exist as dimers. Very important when something is in red, I told you, demonstrating the high possibility or ease of forming two solid, strong hydrogen bonds in the dimeric form. And that is what you have in the next figure therein for this smaller or simplest carboxylic acid. The highly polar carboxylic acid easily dimerizes. So the simple carboxylic acid exists as in their dimer and then the dimerized form, and more so in liquid form. Okay, so we have that over there now, and in non-aqueous solvent like tetrachloromethane, forming two good hydrogen bonding between the pairs. You can see that already shown. Can you see this is the hydrogen bonding here, and this is another hydrogen bonding there? Good. Now, what's the implication of this hydrogen bonding? You will find out that it has a lot of implication. The ease of your dimer forming, the dimer formation in carboxylic acid is what is responsible, is what accounts for observed high, extraordinarily high boiling points in carboxylic acid, especially when you are comparing with alcohols that have similar molecular mass, as high as what everybody shouted, 20 degrees C difference. And let's see the table below. You can see this is a ethanoic acid, glacial acetic acid, having relative molecular weight or mass of 60. The alcohol equivalent is propanol, also relative molecular weight of 60. Both of them 60, but have a look at their boiling point. The one for the alcohol is 97, whereas this is much higher. In fact, approximately 20 degrees Celsius difference. The same thing too. This is propanoic acid with molecular weight of 74, whereas this is this butanol, and molecular is 74 too, but look at their boiling points. Very, very high. But this is more than 20 degrees difference. So why? Why is this? The why is that hydrogen bonding, the dimerization of this carboxylic acid molecules is what is responsible for this extraordinary high, the observed extraordinarily high boiling points in here. Now in water and other hydroxylic solvents, these dimers are capable of dissociating to their monomeric form. So if you want it that way, no problem. Now coming to the physical properties of carboxylic acid quickly. Up to the C10 member, remember the first member is formic acid, second member is ethanoic acid, third member will be propanoic acid, fourth member will be butanoic acid, and so on. So up to decanoic acid, the number 10, they are all what? Liquids at room temperature. So in terms of physical property, whether I bring it out in the exam or not, just know that these ones, the first 10 members of carboxylic acid, are liquid at room temperature. In fact, this second member, ethanoic acid, is known as glacial acetic acid. Why? Because it freezes below 17 degrees C, as it's freezing, and to an ice-like solid. That ice-like solid is referred to as glacial, and that is where it defines its name as glacial acetic acid or glacial ethanoic acid. Now, the lower members have pungent odor. I'm not asking you to get to the lab and start smelling glacial acid. In fact, by the time you put it, it's as if you want to faint. It's choking. It's pungent in you. Now, the first 4 aliphatic members, this one, like we said, are highly miscible with water. They're quite polar, like we said. Likewise, you have your simple alcohols too in terms of their physical properties, since their functional group form hydrogen bond with water, since covalency characterizes higher members, as the ratio of hydrocarbon is becoming higher for the higher members. So due to the high content of hydrocarbon, as the molecular weight increases, the solubility of such carboxylic acid, higher carboxylic acid, are becoming less in water. Your benzoic acid is slightly soluble in water, but readily soluble in hot water. These are common physical properties that I expect you to be interested in just knowing, as if reading a storybook, so that you become conversant. When you know the behavior of your neighbor, you will know how to comport with them. So know the behavior of these carboxylic acids and you'll be able to handle them rightly. Carboxylic acid dissolves in appropriate organic solvent. So carboxylic acid are capable of dissolving because they are organic compounds, they dissolve in organic solvents. Now, more on the physical properties. So in terms of boiling point, generally, like any molecular series, as relative molecular mass increases down the group of the molecular series, what happens to the boiling point? It also increases. So that's definite, that's sure. Aromatic acids, compared to their aliphatic counterparts, exist in their crystalline solid forms with higher melting points. When you compare it with their aliphatic counterparts that have relatively the same molecular weight. Let's not waste our time. Let's go to the third bullet. In the aliphatic series, members with even number, that's so unique. God is so wonderful. Even numbers of carbon in them, they have higher melting point than their members with odd number of carbons. And structural elucidation, Dr. Abuaba will be talking about some of this. I used to handle it in years past. Structural elucidation, utilizing X-ray analysis, there are organs, like especially the spectroscopic aspect, infrared, UV analysis, NMR, and MS. These are also using characterizing and analyzing and identifying our compounds. Now, in terms of density decreases with increasing relative molecular mass. So it's so unique. So for this now, let's go to preparations. And like I said, two broad ways of studying it. We go into their economical way of obtaining them. That's the industrial or commercial method of obtaining a carboxylic acid. And then we move immediately to how we can synthesize them in our laboratories. Quickly, in the industry, we are so interested in the first two members, and also the aromatic carboxylic acid, the three of them. And this is the reason behind this is because of their uses and importance of the three of them. This one here is the formic acid or methanoic acid. This one is the glacial acetic acid or ethanoic acid. And this is our benzoic acid or benzene carboxylic acid. From the nomenclature, you know that very well. So how do we synthesize them? The next figure shows everything. Everybody say everything. Yes, there are three main methods. We have there are three main carboxylic acid that are of industrial importance. The formic acid, HCOH, has this main method of preparation, where you have carbon monoxide reacting with sodium hydroxide under very high temperature, 200 degrees Celsius at high pressure, to form the sodium salts of the acid we're inserted in. And by addition of dilute acid, maybe dilute HCl, you just have it's bringing out your carboxylic acid. This is a very good reaction. Every time you want to regenerate your acid from this metal salts. We will see more of this too in preparations down. But this is of industrial value. That's why we're bringing it up for the formic acid. The next one is glacial acetic acid, CH3COH. And you start this. This is very simple. You know that from even our carbonides. You have the aldehyde that can yield our ethanoic acid, and that is ethanol. Ethanol is the second member of aldehyde. And what happens here? You have this anhydride, ethanol acetate, under magnesium catalyst oxidation, just oxidation of ethanol gives ethanoic acid, very straightforward. And for this one is also oxidation to get the aromatic benzoic acid, which is here. You can use two methods. Well, start depending on your starting material. Very, very simple. This is just hydrocarbon. That's toluene. That is your methyl benzene. Ordinary oxidation will give you your carboxylic acid. And we are in a situation where you have also methyl toluene. This one you also oxidize, get this intermediate, and under organochromium catalysis, you have it giving your benzoic acid straight up. The two of them are oxidation methods for deriving the aromatic carboxylic acid. Not to waste our time. That's the three carboxylic acids that are of industrial commercial importance. Now let's go into how we obtain our carboxylic acids in the laboratory. Wonderful. I'm putting one here as X, but I'm still treat it. And though I'm saying you shouldn't bother about it, but I think you should bother because it's going to give us some derivatives, and which we're interested in. Before, the derivatives were not there, but now I'm going to treat the derivatives too, so it's important, please. The first method here, I have about 6 bullets here, is your very simple method, oxidation of primary alcohols. Definitely will give you your aldehyde, which immediately oxidizes to your carboxylic acid. The next one is the Grignard reagent through Grignard synthesis, and then the hydrolysis of nitrites will easily give you your carboxylic acid. Hydrolysis of your esters too, involving saponification, gives it. Yeah, everybody shouted Cannizzaro reaction. We've seen deep things about this very soon. And the last one there is the synthesis of our benzene, carboxylic acid or benzoic acid from methyl benzene, just the one we saw not too long here. And can you see something like that? So we come to that aspect and we pick them one by one now. Now the first one is no, I don't need to give you so many examples. You yourself get examples. That's homework for you. Homework. Give definite examples. Give definite examples. So give different examples to show that trend. Replace your R with anything, CH3, C2H5, branched, whatever. The method can be used in synthesizing both aromatic and aliphatic acids. So that goes. So you have few examples here. Though I'm giving you as homework again, you may not bother to use mine. Anytime you have primary alcohol, basic oxidizing agent, your potassium dichromate, your potassium permanganate, your chromic acid, all these are good oxidizing agents. Just shorten it as O, capital O in a bracket like this shows oxidation reagent. So oxidizing primary alcohol, why is it primary? Because the OH linked to the carbon of the OH is carrying 2 other hydrogens. Good. So you have your aldehyde, further oxidation gives you carboxylic acid. So if you are starting with ethanol, you result to ethanoic acid, no addition of extra carbon. So it's very straightforward. And if you have any branching in the hydrocarbon side, you still have it at the end. So that gives the debate. Now the second bullet talks about obtaining our carboxylic acid through the Grignard synthesis. And this one is making use of your CO2 in that reaction. Over here, you have your carboxylic acid, you have your CO2, carbon 4 oxide gas, which is gaseous, being bubbled into your Grignard reagent, and on treatment with dilute acid produces our aliphatic acid. Now to prepare that aromatic one, especially benzoic acid, which is a good example, you make use of what? Solid CO2. You don't bubble it as a gas. And that solid CO2, I used it in IITA. I think we used to use it in extraction lab in chemistry before, but I don't think it's available. The thing comes out solid like that, white, solid, very cold system. Call it dry ice. Reacting with your aromatic derivative of the Grignard reagent, we see that just cool, and you have it. And that is it. Can you see? For okay, aromatic, I'll go to the next one and it's going to show me. Okay, So generally for the carbonation through greenhouse synthesis, there's always addition of an extra carbon to the final alkyl group you started with in your greenhouse reagent. That's a good way. Exam tactics. You don't have to memorize. Just take your R and add COH to it. That's all. Once it passes through, but you first form start from the greenhouse reagent, react with the CO2, carbon 4 oxide, under the ethylator, under ether, that's dry one, to make the reaction to go forth. You form the intermediate, which on acid hydrolysis yields beautifully our extra added carbon derivative of the alkyl carboxylic acid. So you have these definite examples. We are starting with ethyl magnesium bromide, and we are ending with propanoic acid, which is the next member, ethyl propanoic acid. That you see. So that is it. If you are starting, like I said, the aromatic form, just get the aromatic magnesium halide and of it. Do the normal thing, but here it is dry ice, not gaseous, as in the earlier one. And still under the same condition, have the intermediate acid hydrolysis, and you have just COH replacing them. So it's quite simple. You don't have to memorize much for your exams. So carboxylic acid now from nitrites. That one too is in fact simpler. Very, very simple. You don't have to memorize. First of all, here you form your nitrile from reacting your RX, haloalkane, with alkali metals, sodium, potassium, the cyanide of it, in aqueous alcohol, and you have your nitrile being formed. We see that very soon in that equation, which is a solvent that can dissolve the two systems. Now, full hydrolysis of that nitrile formed, either in alkali, we give the carboxylate anion, or nitrile hydrolyzing in mineral acid produces the free acid straight up. I've told you, anytime you want to release your acid from the metal salt, you just hydrolyze on the acid and you have your free acid coming out. There is intermediate formation of amide in both cases. So for the aromatic nitrile, benzonitrile, hydrolysis will give our benzoic acid, and that is it. Benzoic acid is over there. I think you are seeing it very well. So you start with the haloalkane, react it with any of these alkali metal cyanides. Under aqueous alcohol, you have your nitrile, which is the starting material, first form. Once your nitrile is formed, ordinary hydrolysis through the pathway of amide, you have the carboxylate. And over here too, you can have an additional carbon. Can you see additional? We started with propyl, we're ending with butyl, butylate form of it. Here, okay, you start straight with the nitrile and the aromatic, and you end up with that. No problem. So another method of synthesizing our carboxylic acid is through the hydrolysis of esters, saponification. This one, you know, tell yourself, I know it. Yes, you know it even from your GSS, saponification reaction. You know it very well. When you get your glyceride, in sodium hydroxide, the sodium salts, saponification reaction, go and revise that one. That's very, very simple. The fluoxene esters in conch, sodium hydroxide. One of my father's senior sister used to say soda in our hometown, and she makes it. She never went to school, and I mean, not on the normal school we have, and she produces this soda so beautiful, even to the point when she was about to die, she was still selling soda. So locally made soaps, and here and there, some of you will go and apply in soap industry. This is the basic reaction they do there, just adding one thing or the other to there. Some of you during COVID-19 or whatever, you were selling liquid soap. It's very simple to do. This is the basic reaction there. So, and treatment with acid will yield your carboxylic acid. So we have it that way. You can see it there. That's saponification reaction. The next one is that Cannizzaro, which I said you shout it and write it down. Cannizzaro reaction. In Cannizzaro reaction, look at the second bullet. We have an aldehyde. That aldehyde, go back to first bullet. That aldehyde does not have alpha hydrogen. Tell yourself, aldehyde without alpha hydrogen. That is the basic condition. So whenever you have aldehyde with no alpha hydrogen, like your methanol, if you write it out, you will see that alpha position, that is position number 2. In fact, there is no position number 2 in methanol. Even in benzaldehyde that has position number 2 is on the aromatic carbon, and you find out that that one doesn't have carbon. So these two systems can easily undergo Cannizzaro reaction. Another name for it is a self-oxidation reduction. It's a self-redox reaction. Why? Because after reacting with your conc alkali, it gives both reduction product, the alcohol, and also the oxidation product. That's it. This methanol. Under that sodium hydroxide, you have the alcohol, and also you have the carboxylic acid. You know, the aldehyde is the in-between. The reduced form of aldehyde is primary alcohol. The oxidized form of aldehyde is the carboxylic acid derivative, and that is it. So that's the unique thing about Cannizzaro reaction. This is showing the aromatic system. Yeah, this is a benzaldehyde derivative, specifically paranitrobenzaldehyde. In fact, smaller concentration of sodium hydroxide. And you see, this is a alpha carbon with no hydrogen. So it will undergo this Cannizzaro reaction very, very easily. You can see it. The alcohol form, which is the reduced product, the carboxylate product, which is the oxidized product. So that is it. The next one, okay, now we have completed preparation of carboxylic acid. We will now come to the reactions of this carboxylic acid. Good enough, I've talked about the structure, hydrogen bonding, and some little chemistry over there. And I want to say that it extends here. When you are looking at their reactions, because we're coming to derivatives of this carboxylic acid soon too, over there, you have, they are capable of forming these salts in them. Very beautiful things like that. That's it. I have about, is this 7 bullets here? I wrote some X, which I may not want to touch because they are, but I think I'm touching them. I have slides to show that over here. Let's just go into all of them. At least if it's not useful for your exams, it will be useful for you in future. Maybe at PhD level or whenever you are a professor somewhere in the world. So I wish you well. Now, the salt formation. For this is an indication of its acidic property. So whenever carboxylic acid reacts with metals, very, very important. You don't have to memorize, just say within you. If I have carboxylic acid, if I add metal to it, it liberates hydrogen, and that is it. I have generalized there. Any metal, reaction with metal, will liberate what? H2, kind of effervescence reaction over here. So you have just the metal salts of the anhydride formed, but don't bother about this detail. So this here, put your R, that's another thing on homework. Put your R. R, definitely I won't give you R in the exam. If it's CH3, don't worry, just put CH3 here, and so on and so forth. That is ethanoic acid. I'm starting with ethanoic acid. So that is one. One of it is, but all of these reactions are showing that carboxylic acids are really acids, because anytime you add metals to acids, they always liberate hydrogen. Effervescence reaction. Remember your GS3, is it integrated science now? Or your SS, even your SS chemistry, objective, WAEC, NECO, you treated all this. So that is basic what is happening. Then another one is that anytime you have carboxylic acid reacting, in fact, that is, well, your 191, this is the practical for 191 over here. But maybe that's why I said I won't touch it as such. 191 practical one, okay. CHE191P. Yeah, so you recall, anytime you have carboxylic acid, you want to test whether it's an acid. Just add some sodium carbonate, that's the formula, take note, or sodium hydrogen carbonate. What do you notice? You notice effervescence. What is coming out? CO2 is coming out. And that proves to you that that compound is carboxylic acid. That's it. So you have it. Anytime it's an acid, you add Na2CO3, sodium carbonate, you have effervescence due to evolving of CO2. If it is sodium hydrogen carbonate, you add, it's still effervescence, you have CO2. That's the complete equation for that one. Now, the next two, what you do in 191 practical 2, with sodium hydroxide, you have your carboxylic acid forming the salt and water only. You know, because carboxylic acid is an acid, you react acid with base to form what? Salt and water only. So recall your neutralization reaction over here. You come, and that is what is happening too. You have your carboxylic acid reacting with your sodium hydroxide to form the sodium salt, that is the salt, and water only. And that's from your GS3, you know that definition for, sorry. So the esterification is the next one we are going into. And for esterification, you know that one straight up. You recall mechanism for forming your ester and water only. How do you get water on ester and water only? Very, very straightforward. You have what? Alcohol plus carboxylic acid to form ester and water only. Now you have carboxylic acid. Just react with alcohol. That's what it shows. And you have your ester and water only. And how you discover it? Ester always has sweet smell. And that is it. So reaction, we recall the mechanism formation of ester, right, from your SS, and water only, from reaction of carboxylic acid to alcohol, involving the alkoxy-hydrogen fission in that case. So this is just an example to show where the water only is coming. You have the OH of your carboxylic acid with the proton H from the alcohol forming, responsible for the elimination of the water. And what joins this ethoxy ion, for this in this example, now joins with that ether linkage over here, and that's it. And you should be able to name this. How do you name it? You end up with the carboxylate moiety. You start with the alcohol moiety. Alcohol moiety here is ethyl. I'm not teaching you nomenclature here, but that's part of it for esters. This will now better, the name will be what? Ethyl. You end with YL on the alcohol side, YL, ethyl, and this is 3-carbon propanoate. So this is an example. That's why I said example. You started with propanoic acid reacting with ethanol. I can give you anything in the exam and tell you to predict the product or give me the name of the ester that is formed. So you should be able to do that. For the aromatic side too, you have your benzoic acid. This is a very simple alcohol. What's that alcohol? That's methanol. Methanol, and then you have the ester that is being formed there. Good. So that's the classwork. I've done it already, so we don't waste our time on that. Now, another reaction. Everybody say acyl chloride. Somebody was asking in the chat on Tuesday that what's our acyl chloride? Yeah, we're coming deep into these derivatives of carboxylic acids, and this is part of it. When you have your, should I just giraffe before we're there? That's acyl group. That's the acyl. When you have R linked to carbon of the carbonyl, then the OH replaced by Cl. That's all. OH replacement by Cl. You have your acid chloride or acyl chloride. That is it. And that is it for your anhydride. OH replaced by this ester group gives you your anhydride. And when it is replaced by an alkoxy, OR prime, you have it as an ester. When you replace it by NH2, that is the OH of your carboxylic acid, you have an amide. Well, let's go back to, we're not on nomenclature yet. We're talking about how the reaction of carboxylic acid. Funny enough, this reaction is also a way of forming one of the derivatives we are highly interested in this course, and that is formation of our acyl chlorides. These are common reactions. Everybody say common. Yes. Whether it's aromatic or aliphatic carboxylic acid, where you have the hydroxy group on the carboxylic acid easily replaced by reacting with all these chlorinated systems. You have the 3 of them. This one is PCl3, which is phosphorus trichloride. This one, another one is PCl5, which is phosphorus pentachloride. And the third one, which is the most appropriate, is SOCl2, which is a sulfur dichloride oxide, or what we simply call thionyl chloride, is for chlorinating our carboxylic acid to give the appropriate acyl chloride. Now, like I said, the most appropriate. The reaction with SOCl2 is the most appropriate, since the other two products are gaseous and can easily be removed from the mixture. So this is more appropriate. And thionyl chloride is also carcinogenic, but notwithstanding, when you put on the normal safety gadgets, for nose, for face, everything, you are maxed up with your lab coat, everything. You are safe to work with it. I've handled it severally in my synthetic chemistry researches. So that is it over here depicted, whether you use the PCl5 or PCl3 on the carboxylic acid, you have your acid chloride, acyl chloride before. That's our target. And the most appropriate SOCl2, we also give the acid chloride. So in exams, definitely don't expect R. So R will be more specific and you'll be able to predict the product of that one. Now, another important derivative of carboxylic acid are amides. And these are easily formed too from carboxylic acid high. How? Just go through and we have the equation below it. At high temperatures, you have ammonium carboxylates being formed. How? From your carboxylic acid and ammonium carbonate. Ammonium carbonate is NH4 brackets, 2 of it in a bonded to CO3. That's your ammonium carbonate reacting with your carboxylic acid to first form the salt, ammonium salt, ammonium carboxylate salt. And then with the presence of some of this acid you started with, you see you have your amide before. Amide is CONH, NH2. The H will be replaced with alkyl group or other groups, but that is basic formula for amide groups. So, and in a system, okay, let's just finish reading the bullets. So the ammonium carboxylate undergo dehydration in the presence of free acid, which you have just seen in the second time, the reaction to give the amide which we are interested in. But when the free acid, take note, the free acid is very important for you to arrive at the amide here. That is, you make use of excess carboxylic acid when you're starting your reaction. Some of them will be converted to the carboxylate derivative. And then the free acid that is left is important because if it is not there, the formed ammonium carboxylate will just dissociate on warming, and that is what you have. If with no free acid, absence of free acid, dissociation will occur. You have a return back to sender, your acid being formed there. So, which is not our desire. So we have talked about how we form these derivatives of as well as reactions of carboxylic acid. So you can easily obtain our derivatives through the reactions of this carboxylic acid. Well, this is what we are supposed to have first considered in terms of getting our derivatives. Sorry. I want to see if I can. Okay, if I can. Okay, I wanted to lessen. Okay, no problem. I wanted to show this proper. Trying to see. Oh, no. Let me go back to my Zoom. Sheets. Okay, good. So I wanted to show the acyl group that person was interested in. So that's the acyl group. And it's just the carboxylate group. But instead of the OH here, we now replace with appropriate substituent to have these 4 derivatives. The derivatives, when it is acyl chloride, that OH is Cl. When it is acid anhydride, this one is RCOO, 2 O's. When it's ester, you have R prime CO. Then when it's amide, you have NH2, derivatives of it, and so on and so forth. So let's see it proper. Following are the derivatives. This will be the acyl chloride. This will be the anhydrides, and then acid anhydrides. This will be for the amides, where the NH2 could be NHR prime or NH R prime, two of it, or the arrows could be different, depending, and that gives the amide. And then the ester form is the OR there. So the one I was showing you earlier, and that is just it. When you have the OH replaced by Cl, you have your acyl chloride, and that's the general formula for it and structure. When you have it replaced by RCO, we have the acid anhydride, which is like duplicating the effect as if they are the same. That's element of symmetry somewhere here. That's another part of chemistry. Let's leave symmetry. That's not what we are into. Maybe next year I can introduce that one to your junior that are coming after you. So we have the OH replaced by OR prime. You have your esters, and then for this, the amides. Yeah, we're rounding up gradually. Now let's do a kind of general comparison among these four derivatives of carboxylic acid. Everybody say the four derivatives. Yes, the four derivatives that we have mentioned, they are all polar compounds. And let's look at their general properties, physical, chemical, and whatever applications. Apart from amides, that we treated four of them. So the other three, that is the acyl chlorides, acid anhydrides, and the esters, they have normal boiling points that are similar to their counterparts, having relative molecular weights, same molecular weights in the aldehydes and ketones. They have almost the same. But for the amides, it's a little different. And why? The amides possess some kind of intermolecular hydrogen bonding. That's why it's a little different. So they therefore have fairly higher boiling points, and they do exist too as solids. So this affords amide to be more soluble in water than their other derivatives, acyl chloride, acid anhydride, and the others. Now, in terms of electronegativity among these four, the trend is that the acid chlorides are the most electronegative compared to the acid anhydride. Next is the acid anhydride, and then we have the esters, and lastly the amides. In terms of reactivity of the derivatives, the most reactive are our acid chlorides, just like most electronegativity, followed by your anhydrides, followed by your esters, and followed by amides. So in terms of electronegativity, it's also an eye opener to the reactivity, that is electronegativity and reactivity. But those trends are important. Yes, I've treated some of these structures into two, some of the properties into two, and some of their preparations and reactions to treated, but I still want to check them up. Everybody say check up. Yeah, check them up. And then maybe their naming, we've not really gone into the deep forms of their namings, but we've treated the other bullets over there. I'll try and check on your charts and see what you have for me, but make sure you write your attendance, your matric number, your department, your name, and just hi me. And then at the same time, next week, Dr. Ababa will be coming to take up the class. There is an hand raised. Maybe, I'm not too sure if I can give you attention, but let me go through your charts generally. So, little by little, that is the end of my own part, and which I know you must appreciate me. Can you clap for me there? Let me add clap if you are not clapping for me. I think the charts may be more important. I will put clapping system later to what I have there. So that's the end. Okay, let me check on your charts. Okay, thank you. Thank you for good comments. Well, who is that? Yeah. Thank you, Ma. Thank you for thanking me. Thank you. Yeah, good morning, Ma. Thank you so much, Ma. Thank you, Ma. Thank you very much, Ma. Thank you, Ma'am. Well done, Ma. You have done a wonderful work. Thank you. Thank you, Ma. Thank you, Ma. Thank you so much, Ma. Yeah, in fact, I have some fine emoji here with glasses. I hope my own glasses is not dark. No problem. I still accept that. Thank you, Ma, very much. We really appreciate. Thank you, Ma. God bless you, and you too. Thank you, Ma. May God bless you abundantly. Thank you too. Good morning, Ma. Can carboxylic acid react with ether? Ether is a good organic solvent. Yes, a good organic solvent. Carboxylic acid are not good organic solvents. They are more or less reagent. Ma, why is this the end of your part? Well, but you are funny. We love you. I love you too. Thank you. Thank you, Ma. Thank you very much, Ma. God bless you. Nice to play at the end of the course. Thank you, Ma. Thank you, Ma. Thank you, Ma. God bless you, Ma. Thank you, Ma. Yeah, nice comments. I'm seeing so many departments here. I'm clapping already. That's great. Thanks for clapping for me. Thank you so much, Ma. Great. Thanks so much, Ma, for the lecture. Chemistry is full with you, Ma. Yeah. Chemistry is full of excitement. There's a book that I normally recommend many years ago, 5-6 years ago, and that is Chemistry, the Central Science. If you want it, I think I'll recommend it for you. You can get to former Longman, now something of Learn Africa. Just go to their a challenge around Filade Street, Filade Mabu something company, that street. You have their the publishing farm. Get there, they will give you the price you can never have anywhere in Ibadan or even outside. So you go there, just mention Chemistry 176 class in UI, recommended that they should sell it to you. Your class reps can see me and I can give you a note to them. Chemistry, the science teacher, is so good, so good. It's good not just for now, it's good generally for other chemistry courses and in life, not even on first degree, masters. Thank you, Ma, for the classes. That's good. Yeah, a lot of departments. Yeah, your CA will be coming up soon, please. We're going to announce that by next week. By next week, your CA will be coming up. The mode, I don't know. Thank you very much, Ma'am. Great. I don't know the mode yet. I wish, like JAMB exams, when you are with your laptop, you can have it. I don't know. I'll try to see what we can do to make sure your CA comes up next week, please. Get set to it. Class reps, be at alert so that once I put the notice out, you come for your exams. It's not going to be difficult. It's going to, like, it's a continuous assessment. All the assignment I'll be giving you is what will come from my part, and I'm sure what the other lecturers too. Ma, please, can we have the recording on YouTube? It's already on YouTube. Who is that? That's Messi or Yawole. Yeah, it's on YouTube. Just access the link. The link is there. Is it not? Please do that. Can I have other comments? We have just 5 minutes more and I'll end the whole class. I'm trying to look at your charts. Wonderful names, nice names. It's okay, Ma. Great. Yeah. Lots of departments. Yeah, I think. Thank you, Ma. Okay. Thank you too. I'm trying to see if I have any unique question here. I don't see, I think I've answered all your questions. Good morning, Ma. No problem. Thank you for greeting me. Any other information? I can see 2 people using the same laptop, no problem. The most important is you have registered your attendance. That's okay. Chi. People are dropping out already. Okay. So you have your YouTube You have your YouTube link, access it, download it, store it in your laptop, store it on your phone, press it anywhere instead of wasting time looking here and there. I need to check on my YouTubes that you have. It's going to do you good. So here comes the end of my music here. I hope you all know that I love music. I love music. Yeah.